It's Wednesday evening, 7:30 p.m. AWST, and you know what that means. It must, of course, be the ICRAR Astro 3D Weekly Astro Talk. Congratulations on finding us once again. And if you're watching us in the future on a rerun, hello. I hope the future is better than it is today. So first things first, I would like to acknowledge the traditional custodians of the land on which we're speaking today. This, of course, is the Whadjuk Noongar people, and we pay our respects to the elders past, present, and emerging. Now, who are we? We are ICRAR, which stands for the International Centre for Radio Astronomy Research. We're a group of astronomers from Curtin University and the University of Western Australia, searching for the hidden aspects of the universe through radio astronomy, all very exciting. And also, we are Astro 3D, the ARC Centre of Excellence in All Sky Astrophysics. Over 200 astrophysicists spread across Australia, hunting out all sorts of cool things like matter and light and elements of the Big Bang, from the Big Bang all the way to the present day. So just a very small area of study there, just a tiny, tiny thing. I'm sure it's all been answered. There's nothing more to really worry about. But to answer these incredible questions, tonight we have with us Dr. Claudia Lagos. Dr. Claudia, how are you?
Hey, good, all good.
Excellent, excellent. So can you give a quick rundown on who you are and what you do?
Sure, yeah. So my name is Claudia Lagos. I'm a researcher at ICRAR and Astro 3D. I'm actually a theoretical astrophysicist, and part of what I'll talk today is about how we simulate the universe. So I'm actually originally from Chile, not from Australia, although I did become Australian earlier this year, before the
congratulations.
So, you know, double nationality.
Passports for days. So the first thing we're going to look at, of course, is sometimes in science, we get to make these beautiful graphs and plots and pictures, and it's hard to know whether it's science, whether it's art, or maybe it's a bit of both. Maybe science is art, art is science. It's all the same thing, probably on some grand level. So let's have a look at our first and only, I guess, today, science or art picture. All right, let's have a quick look, everyone. Spend some moment pondering this thing. Goodness me. Okay. Do you have any idea, Dr. Claudia, what this might actually be?
I have no idea, but I've got to say it's a little bit unnerving, right?
It's not. Yeah, it doesn't. Whatever's happening is probably not good. I think it's like it looks like the sun maybe, or it's a star, or it's something like that. It could be, and I'm gonna say something about black holes because I'm a simple man. I see a black hole in a thing and I go, it must be about black holes. That's my only guess. That's my big scientific take on this, but I don't know. So our audience, if you're out there, what do you think it is? You can always write it in the chat right now, or you can always go onto @ICRAR on Twitter and answer it there. And on Friday, we'll let you actually know what it is. I actually have no idea what it is. Dr. Claudia, do you know what it is? You don't know what it is? No,
got no idea.
We're going to say science.
Very interesting.
You'll need to come back. Wonderful. Yeah. You need to come back, people, and find out.
Science, but just a gut feeling. I don't really know.
Okay. All right. So whilst Dr. Claudia is chatting, you'll be able to ask questions in the chat, and I can ask them at the end. So feel free to write down your questions, anything you like in there, and we'll do what we can. But I will pass it over to Dr. Claudia.
Right. Thank you, Greg.
You can ask them
all right. So I'm going to take you to a little bit of a trip about how do we simulate galaxies and why is it so similar to actually baking a cake. So I want to start with the beginning. Astronomy, I think it is actually these fascinating fields, right? I think when we see these kind of images of the night sky, we all get fascinated. And I think this is part of why we do what we do and why we want to understand how is it all these stars form. What you see here is actually part of the Milky Way and how these galaxies form, right? That is the question. Now, we've got amazing images of the universe. This is one of the deepest images that we've been able to obtain. This is from the Hubble Space Telescope. And there's a lot of information here. So some galaxies are very clear here. And you can see, all sorts of shapes and colors. You can see some of them are relatively round and smooth. Some other ones actually have a lot of features. You can see these ones here, for example, just having these arms. And all of these are actually galaxies. So we want to understand how they formed. Now, all of the galaxies that you see here are relatively nearby for at least astronomical standards. But there's some very puzzling things in this field here that you probably can barely see and are highlighted in these little squares and are these very, very red compact objects here. These are actually galaxies. But these are not just any galaxies. These are incredibly distant galaxies. These are galaxies that are roughly 0.5 billion years from the Big Bang. And considering that the universe, we think, is 13.6 billion years, these are among the first galaxies that we can observe. So this means that we can see galaxies all the way from our own Milky Way and nearby galaxies to almost the time of the Big Bang. So this is what we want to understand. So the fundamental question then, we want to understand how the universe evolved into producing all these types of different galaxies that come in all sorts of different shapes and colors. And this is the picture that we have of how our universe has evolved. So this is going to be very qualitative, but it all starts with the Big Bang and the first light that we can actually observe, which is the cosmic microwave background. This is relic radiation from the time of the Big Bang. This is the first time light can escape, and this is actually radiation that fills the entire volume of the universe. Now, something that is very interesting about this radiation is that when we see different parts, you see these parts that are blue or red here, these are extremely similar. So we're talking about differences here of 0.00001. Now, between this time and the time of the formation of the first stars and galaxies, there's a period that we call dark ages because no stars are yet formed, so there's nothing shining. But after that, galaxies start forming, and eventually they evolve into what we observe today, including our own Milky Way. Now, the interesting thing, of course, is that nowadays we see galaxies of all sorts of different morphologies and different sizes and colors. These are all galaxies, okay? So somehow, at a very fundamental level, they all follow the same physics. So it's just like cakes, right? All cakes, at the end of the day, are made up of the same components, but they end up looking very different. So what is these different components that we want to include in our cake or our galaxy, in my case? So these observations of this relic radiation from the Big Bang tell us a very compelling story of what are the constituents of our universe. So from that, we understand, if we look at the total energy of the universe, we understand that 27%, so this part here, is made of dark matter. Now we call dark matter dark because it doesn't shine, it doesn't produce light, but we see its effect because it interacts through gravity with normal matter. Now you have this massive part that is dark energy that we understand in the effect it has on the geometry of the universe. We know this is what produces the accelerated expansion of the universe. And we have this tiny 5% that is ordinary matter. This is what we know. These are the stuff that we can see on Earth. So this is all the atoms that we know about, and this makes only 5%. But actually, when you want to understand how stars form and galaxies form, this is the super difficult stuff, because this kind of, this ordinary matter has a lot of physics that becomes relevant there. We said dark matter is gravity. Dark energy is some form of negative pressure. But ordinary matter interacts in all sorts of different ways. So this is the super difficult stuff. So making galaxies is just like, of course, the theme of my talk, making a cake, of course, right? Except that you don't have a recipe. You only see the end result, and you need to figure out how you got there. But it's not just any cake, really. It's actually a very complicated cake. So you see the end result, and you need to figure out how you got there. Now, it's not just one single cake, right? We want to understand every single one of them and how the ingredients were mixed up in a way so that it produces the kind of galaxies that we see or the cake that we see. So let's break this down. Let's go through baking. So let's start with our cake. We're trying to decompose this, okay? So let's think first about obvious ingredients that go into a cake. I would say, okay, we have our galaxy. Our galaxy is going to be a cake. First ingredient, obvious to me at least, is sugar, right? I mean, a cake has to be sweet, or at least some form of sweetener, right? Very important. Now, when we see in our galaxies, a nice parallel to this could actually be the stars. So the stars are to a galaxy like sugar is to a cake. Now, if we look at stars in galaxies, they come all in, again, in different sizes and different colors. And here I'm highlighting just different types of stars. So what you see on the right, in this part here, these are very young, bright stars. And when you see in this other part, that's very typical of what we observe in the centers of galaxies, are very old stars. Now, we see stars all across galaxies, okay? So they're an extremely important component. Another important one is flower, right? Now, for me, flower is like the regions where these stars form. So the reason why you have all these stars is because at some point they should have formed in your galaxy. We do see these regions of star formation in galaxies, and I'm highlighting just a few of them. They produce generally these spectacular images that we get from the Hubble Space Telescope. You can see in this case, actually, you see all these this color smooth part. This is actually dust, interstellar dust. So that's very, very interesting, very puzzling. It's not exactly like the dust that we have to get rid of in our homes, but it's dust nonetheless. And what you see here in the little points, these are actually newly formed stars. So these are the places where stars form. And you can see similar things here, stars being born, embedded in this flower, in this part of galaxies. Now, something very interesting about stars is that if you happen to have a massive star, they end up their lives as supernovae. So let's take this young region. We have this region where stars are being formed. Some of these are actually very massive stars. What happens to massive stars is that they evolve very quickly and they end up exploding as supernovae. And that produces these stunning images. So all of these are actually bubbles that are produced around supernovae. Now you have to think that in one single galaxy, you have billions of stars. So in principle, you can have many of these supernovae going off at the same time. So we're talking about a single region in a galaxy. Now, what happens when you actually have many of these supernovae events? Something very fascinating can happen. You produce actually these incredibly large plumes. This is actually the image of a galaxy. What you see in red is all this dust and gas that is being expelled out of the galaxy due to the effect, the energy that is being produced by supernovae that is so large that it ends up pushing away a lot of the material that is in these galaxies. This is actually a very important ingredient in galaxy formation that we find. So stars play the role of producing all the structure that we see in galaxies, but it's also responsible for producing this type of phenomena, these large plumes taking away a lot of the material from the galaxies. Let's move on with our cake. So we have sugar, we have flour, we have stars, we have star-forming regions. Let's look at another possible obvious ingredient, butter. So not all cakes actually need butter, but many do have butter. And a similar thing happens to galaxies. Not all galaxies have supermassive black holes, but when they do, they can make spectacular changes in the galaxy. So many of you might think we haven't observed black holes because they're black, right? They swallow all the light. But actually, we have a lot of evidence of the existence of supermassive black holes around in the centers of galaxies. This is actually an example of that. This is real observations showing how this is water, actually, how water is rotating around a supermassive black hole in an external galaxy. And because water behaves very much like a laser, you see a single frequency and you end up reconstructing fully the accretion disk around the supermassive black hole. Now, around our own Milky Way center, we know there's a supermassive black hole because we can see the orbits of stars around this center that is empty in principle because you don't see any light. But you can work out the effect or the amount of mass there from the motions of the stars. So we actually see supermassive black holes in many galaxies, pretty much all the large galaxies that we can observe. And they can also produce spectacular changes in galaxies, and that's shown here. So a supermassive black hole is so large, so we're talking about roughly 1 billion times the mass of our own sun in a single object. And they can be so energetic in so many times, only that the central black hole outshines the galaxy, that they can again produce these large plumes and remove a lot of the material from the galaxy, so changing the fate of this galaxy. So that they play, again, a very important role in shaping our final cake, our final galaxy. And of course, any cake, or at least a beautiful cake, needs some colors. Now, colors for me are these spectacular processes that we observe. So galaxy mergers are the collision of one or more galaxies that produces these stunning morphologies. So all of the images that you see here are collisions of galaxies, and you can see in some cases, these are approaching to each other. In some cases, you can see they're already in the process of collision. And this creates among the most fascinating images that we can see of distant galaxies. Now, not all galaxies go through this, and therefore I put it in the part of colors, because not all cakes need color, right? And let's talk about our final ingredient, something that keeps a cake together, X. So X, in this case, what keeps a galaxy together is actually dark matter. So we already saw early on that dark matter is a larger fraction of the total matter in the universe compared to our normal matter. That means that the gravity of a system is actually dominated by this dark matter. Now, although dark matter is dark, we can see its effect through gravity, and this is what you see reconstructed here. So all the blue diffuse part is showing you where dark matter is. And we know it's there because we can see how the background light gets distorted by the effect of dark matter, because it's so massive that the light ends up actually going around, and we end up seeing these beautiful arcs. I'm going to point out some of these. For example, this one here, that is simply the effect of a massive object changing the space and producing the light to bend. So this is, to me, the X, because this is what keeps the cake together. And this is what keeps galaxies together. All right, so let's move to the oven. We've got all the ingredients. We now need a very good oven. In our case, that means a supercomputer. This is actually an image of one that you can find here in Perth, in the Curtin campus. So it's a very powerful supercomputer with 2,000 roughly CPU cores, and ever growing. It's going through a nice upgrade, so we can do even more powerful simulations later this year. And this is going to be our oven, okay? So let's see what we get with all these ingredients. So what I'm going to show you is a few images from a real simulation of how galaxies form in this universe that is dominated by dark matter and dark energy. So very early on, the universe is very homogeneous. We know that's the case because of the cosmic microwave background. So let's move forward. As time goes by, what you see actually is the collapse of these structures, the formation of this cosmic web that is very similar to a spider web. But something that you start to see, for example, already in this image, is these little bubbles here. These are actually the largest scale effect of many supernovae going off at the same time. So it's that 5% that we said making a huge effect, even on very large scales. So we see those bubbles growing, and we move forward, and we see this, you know, a single galaxy would be a tiny point in this image. So we see now this very large bubble in this case is actually produced by a supermassive black hole. So again, what's going on inside the galaxy is making a huge impact in the galaxy and even beyond. that galaxy. So let's move forward. The cosmic way keeps collapsing. You end up with these regions that are very empty. So the black here is very empty regions. And if we continue to move forward with our simulation, we see more and more of these little bubbles forming that are produced by our stars inside the galaxies, but expanding to much larger scales. And we end up with this picture of the universe. Now let's look at an individual galaxy. So this is the same simulation, but now what I'm going to show you, I'm going to zoom in into an individual region where one galaxy is forming. And this happens to be a galaxy similar to our Milky Way. So let's go inside. Early on, this looks nothing like the kind of galaxies that we observe locally. So this, for example, has a lot of structure. You see a lot of little dots here. There's not really any spiral arms. But as time goes on, what you can see, you can already start to see a little bit of the normal familiar features that we see in galaxies. So you can start to see a little bit of spiral arms, but this is a very active environment. You can see all these little things. These are actually individual galaxies. So there's a lot of collisions going on here. But eventually this settles into a nice disk, exactly like our Milky Way. So now what I'm going to do is to show you how this would look like in stars only, because here what you see is only the gas. So this is how it could look like in stars. So very nice disk, very similar to our Milky Way. Now, I came back to the gas there so that you can see the spiral arms in these galaxies, and I'm going to zoom out because these are very large simulations where we can produce different types of galaxies. And eventually, I'm going to fade in to only show you where the dark matter is. So this is now only the dark matter. Now, you might ask yourself, okay, we can see you produce a single galaxy, but what about this whole business of different types of cakes and the different types of galaxies and all these different morphologies? So let me show you how we've improved over the years. So I'm going to start with 75. So this is the first supercomputer, Cray 1. By that time, roughly that time, this is the kind of simulations that we could do. And you can count, if you want, with your hands, all the particles that are involved in the simulations. Now, if we move forward about 20 years, we have improved now supercomputers by a factor of 1,000. And this is the kind of galaxy that we can do. Still doesn't look much, right? Like a real galaxy. Now let's fast forward into nowadays. This is now the largest supercomputer in the world. Now the improvement from the 93 one is this time a factor of 1,000,000. And now this is the kind of galaxies that we can do. So you can see that in a scene with the same ingredients, so you have to think below all of this is the same ingredients, our sugar, our flour, our butter, eggs, etc. And you can produce all these different galaxies from something that looks like a disk, a nice disk like the Milky Way, to something that looks very smooth and spherical. So let's look at some of these ones. All of these galaxies are actually simulated galaxies, and you can see the diversity of those that we produce. Now, what you start to see now is real galaxies. So I chose these ones so that you could see the comparison with the simulated ones. So you can see the ones here at the top. These are all what we call elliptical galaxies, and these are very similar to the ones that we produce. Now, if you move down to the ones that have spiral arms, we can produce that kind of galaxies here. And even these peculiar ones that look more like an S, these are galaxies that are in a collision. We also get those. So that's, I think, a real success in all this story. However, making simulated galaxies is actually very difficult because there are many, many physical processes that we have to consider. And we know we probably are missing many. So this is usually a work in progress. So similar to our cake, although we can have the ingredients, we don't always know how to put them in the right order. So this is the same as trying to get a nice cake and doing your best effort and sometimes not necessarily succeeding, but getting close. So this is our work in progress. And with that, I'm going to take your questions.
Thank you very much, Dr. Claudia. That's very good. Poor Elsa. Poor Elsa. We haven't quite made a proper Elsa yet in space. That's fine. We'll get there.
We'll get there, yeah, eventually.
What do you think we actually need? What is it? Just more computing power that do we need to make it better, or is it? I mean, is it a secret ingredient? Is there another ingredient we need to add that you're like, oh, that will make it much better?
Yeah, I would say both.
You say both?
So, yeah, unfortunately. So we know that the computing power has definitely been essential in getting to the point we are now. But we're probably hitting more a stage in which we have to be smart about the possible missing ingredients that we have to still explore. We don't know whether they can make huge differences or maybe be important in some specific cases, but at least our efforts are going usually in both directions, trying to be smart about the algorithms and using better our computers, as well as thinking of these missing ingredients.
Fair enough. There we go. It's always more power. More power is what we need.
More power, more money, more money.
We've got a lovely comment from Suhail saying, excellent talk, I'm amazed at simulations. And the question is, do you feel that quantum computers will be used to make simulations in the near future?
Yeah, that's a good question. That's still, I think, being explored because it's not absolutely clear that the uses of quantum computers are going to be well targeted to these kind of problems. Similar to what you think about, say, GPUs. GPUs are very good at making small calculations very fast and many times. So for these kind of issues, they might not be exactly the best tool. And same with quantum computing. I think it's going to be a bit more obvious when they develop a bit further whether we can actually use them for this.
Excellent. Okay, there we go. Another question from Chile, also from Chile. So thanks for the nice talk and the analogy. How will the LSST help to the bakery company?
Oh, well, yeah.
What is the LSST?
Yeah, so for people that don't know about the LSST, this is going to be a huge telescope that is almost ready, actually, built in Chile. LSST is really going to explode all the possible cakes that we can get. And I think it's going to reveal probably some galaxies that are puzzling and are going to be difficult to explain. So I think it's really going to be important to give us a sense of the true diversity that we have of galaxies, not just locally, but actually going back in time quite a lot and really get a sense of all these snapshots that we need of all our different types of cakes that we have.
Fair enough. Question from Ian. Hi, Claudia. How big a block of space do you need to include in the model to get a realistic population of galaxies?
That's a very good question. So all of these are actually based on what we call cosmologically representative. That means that it has to be large enough to contain a variety of different galaxies. So for example, we know that the ones like the one I'm pointing out here, this is an elliptical galaxy. These are very rare in number. While something more like these ones here that are more fluffy, these are very common. So that means that we need a large enough volume of the universe to get these rare things. So I'm not going to give you an exact number because I don't know how meaningful that would be, but let's say it has to be big enough to get a good representation of the rare objects.
Fantastic. Thank you very much. Any more questions? While you're thinking of them, I just want to point out that the Australian Dark Sky Alliance needs you, listeners. I'm pointing at you and listeners and viewers, sorry, not just listening as well, viewers. It's basically to take part in the world's largest online sustainability lesson about light pollution on on the 21st of June. You can be a world record holder and help scientists around the world map light pollution and the effects on the environment. And you can go and look at the world record light and at thinkific.com. Just type in world record light and you'll find it, Australasian Dark Sky Alliance. Or you can have a look at the notes down here on our page as well, and down there. So you could do some real science on the 21st of June, on the longest night of the year, down here in the excellent southern hemisphere, the best hemisphere, I think. Between the two, it's definitely the best hemisphere, and we can help us work out light pollution. Alrighty. Well, our listeners have obviously, God, I keep saying listeners, our viewers, this whole new cool thing called visual representation. Our viewers are obviously just too excited. They can't ask any more questions. So we're going to end it there. Dr. Claudia, thank you very much for coming tonight.
Thank you for the invitation.
And we'll see you all next time.
Bye.